Okay, whether they can hear.
Yeah.
Yeah,
Maybe
thumbs up.
yeah.
Oh, okay.
Maybe his microphone's better.
Right, I see a different screen than over there. All right, so we're going to move towards talking about relaxation. As I said, today will be an introductory lecture on relaxation, and then Anne will diverge the tensors and solid state, but the tensors will also get us ready for more detailed relaxation treatment. There's, as always in NMR, a fair amount of math. On the other hand, I think for relaxation theory, there's basically 2 or 3 key concepts. And after that, it's a lot of numerical analysis, which of course is all doable by computer these days. So I'll emphasize when we get to the couple of qualitative insights that I want you to remember the rest of your life. And we'll get one of them today and one of them after Anne lectures. I've been in the process, so next week I teach relaxation in Brazil, and I've been in the process of trying to switch the notes away from PowerPoint into R Markdown, where I can embed some of the calculations into the notes, rather than having things scattered all around. So if you're interested in seeing how, like, today's lecture was generated, let me know and I can upload the R Markdown files to the Dropbox. So far, we've talked about what would be called first order spectra. The first order spectra are where the resonance lines are, what the multiplet structure is, where the resonance lines are. The second order, what's called the second order spectra, determine the line widths. And of course, we're quite interested in both. So in addition to line width, of course, there's the recovery back to Boltzmann equilibrium. We typically have to signal average. So one has to leave a delay between executions of the pulse sequence, usually to allow some degree of Boltzmann equilibrium magnetization to be recovered before starting the next scan. And of course, for those of us interested in dynamics of molecules, we'll see that the dynamics of the molecules are what determine relaxation rate constants. So if we can measure relaxation rate constants, we can hope to learn something about dynamics of molecules. And of course, if you're a graduate student trying to get out of graduate school, relaxation determines how fast you're going to get out of graduate school. If relaxation properties of your molecule are favorable, life is good, and if not, life is not so good. And again, you've seen this picture before, just to point out that even in a 1D of ubiquitin, we can see there are differences in line widths. Some of those differences are unresolved scalar couplings, but some are due to dynamics. In this case, rapid rotation of a methyl group has a dramatic effect on narrowing a resonance line compared to a methylene group that isn't rotating so quickly. And again, just to review, in the beginning of NMR, Bloch suggested that there were two simple rate processes, one that restored magnetization back to Boltzmann equilibrium, which he called longitudinal relaxation. It's also called spin lattice relaxation because, as we'll see, it requires exchange of energy with the surroundings, which in NMR are called the lattice. And the other is basically a dephasing rate constant that destroys coherences or transverse magnetization, and he called this R2. These are usually used to refer primarily to transverse magnetization or Z magnetization, but usage gets a little loose and people might say R2 for double quantum coherence, even though that R2 will be different than the R2 for single quantum coherence, as we'll see. This is just to remind you that the block equations look like this. And if we do our usual transformation into the rotating frame, we have the rotating frame block equations. And if I don't have a radio frequency field, and for a while I'm going to pretend I'm not turning on an RF field, we have free precession, and then it'll be convenient for me to think in terms of raising and lowering magnetizations rather than Cartesian. And then you can see in this case, the block matrix is diagonal. So the plus or minus coherences just decay exponentially to 0, and Z magnetization decays to Boltzmann equilibrium. So here, delta MZ is the difference between the instantaneous Z magnetization and equilibrium Z magnetization. And I've written it this way just to emphasize that Z magnetization always recovers back towards Boltzmann equilibrium, so that the deviation from Boltzmann equilibrium becomes 0. And again, this we looked at already. Fourier transform of the free induction decay gives the absorptive line shape. And then if we analyze this equation for the absorptive line shape, we see that the full width at half height, what spectroscopists call the line width, is 2 times R2 in angular units, or if we divide by 2 pi, R2 over pi in hertz. That's, of course, of great importance to you as a spectroscopist. R2 determines how broad the lines are. And the smaller R2, the narrower the lines. And variously in the notes, I might say line width is R2, but I really mean R2 over pi in hertz. And again, we have very simple 1D experiments for measuring rate constants. So inversion recovery, 180-degree pulse inverts magnetization. There's a time delay, and then a read pulse to convert Z magnetization into transverse magnetization. And I think maybe I showed you this already. So here's ubiquitin. At time 0, the magnetization is inverted. So I phase the spectra to be upside down. And then as time goes on, the magnetization gradually comes back to Boltzmann equilibrium, and now it's right side up. And you can see, for example, here, the delay of 1 second, the aliphatic spins are right side up, but these aromatic spins are relaxing a little more slowly. They're still upside down. And I picked this methyl group and plotted the intensity as a function of time, and I can fit an exponential and get a rate constant. And of course, later on in practical applications, one will do this in a 2 or 3D sense so that we can get resolved relaxation rate constants for individual spins, which I obviously couldn't do for most of the resonances here. And similarly, the classic experiment for measuring R2 is to use a spin echo to get rid of the chemical shift and then change the spin echo delay in order to measure a rate constant. This is a little bit tricky because, of course, you know that if this 180 is non-selective, then the J coupling is going to evolve as well. And one would have to worry about the effects of J coupling on the evolution, or one might hope that this is a selective pulse in some way. And hopefully, I did this experiment, I actually can't remember, but hopefully I did it with some selective pulse on the amides in order to eliminate the effect of the J coupling from the alphas, which would be the main J coupling to the nitrogens. And here's the spectrum at a short spin echo delay and a longer spin echo delay. I didn't try to work on any resolved peak. I just roughly estimated the decay for the whole envelope to get a decay time of about 9 per second. And that would suggest that the average amide proton line width is about 3 hertz if I divide by pi. All right, that's just introduction. So now we want to think about where relaxation comes from. And as I probably told you in class 1, the spins aren't very smart. They know how to spin magnetization processes around the instantaneous magnetic field. So that's this equation. The change in the magnetization, the time dependence of the magnetization depends on the cross product between the instantaneous magnetic field, here measured, multiplied by minus gamma to be in angular units, the cross product with the magnetization. And the important thing is the field is the sum of all the fields. So we have a B naught field, and in the absence of the RF field, we have any local magnetic fields internal to the molecule. For example, if we think about a nitrogen 15 spin sitting here, there's the big B naught field that I've shown in blue. If it's an amide nitrogen, it has attached to it a hydrogen, and that hydrogen is spin 1/2. It's a dipole. It generates a dipole magnetic field, just like a little bar magnet would. And in elementary school, you probably had a bar magnet and then some iron filings, and you see the field lines. So I've drawn the field lines here. So the nitrogen sees a little magnetic field from the hydrogen. And there also may be nearby some circulating electrons in carbonyl groups or aromatic groups, to be the most prominent examples in a protein. And those circulating electrons also generate a magnetic field that would be felt by the nitrogen. So the nitrogen, if we just focus for a moment on the Z component of the magnetic field, the nitrogen instantaneous frequency is the sum of the frequency it has from the B naught field and the sum of all the Z projections of all these local magnetic fields. And here I've drawn the picture so that they all add up together, the blue, the red, and the green, so that the effective field at this moment in time is larger than omega naught. So the instantaneous precession of that amide magnetization would be greater than omega naught. The rotation, if we had transverse magnetization, the precession frequency instantaneously is larger than we expect. But in solution, the molecule tumbles. Oh, and I can then write that the instantaneous frequency is omega naught, the Larmor frequency, plus a difference frequency, delta omega z. I can always do that. A little while later, in solution, the molecule rotates. And if the molecule is rigid, which we'll assume for the time being, then the orientation, for example, of the NH vector will have changed. And actually, I didn't make a very good picture of the electric fields. Anyhow, this vector sum is now different. So here I've drawn the vector sum, a new vector sum, and you can see if I project over to the z-axis, now the z component is about equal to omega naught. So the precessing magnetization has slowed down and is approximately omega naught. I'll point out that in solution, tumbling is going to cover all orientations, so that we're going to have all possible vector sums, and then there'll be some isotropic average, and then deviations from that average. So the average of the deviations averaged over all orientations in solution is always going to be 0. So what I call the Larmor frequency in this case, or the chemical shift, is really the isotropic value averaged over space. And when Ann introduces tensors, this will all come up, that there's an isotropic value of the tensor and then fluctuations around that isotropic value. I can always write this, that whatever the average of the time-dependent Z field is, there's some average value plus the deviations, and the deviations will go to 0. If for some reason I set this up, a problem up, and the deviations didn't go to 0, I would say, well, I just miscalculated the average. And I would then redo the average so that the part that survived averaging was now lumped in to the average to make sure that the average of the fluctuations went to 0. And a little while later, there's a new orientation, new fields, new vector sum, and now the magnetization is processing a little more slowly than it should. So while the molecule is tumbling, transverse magnetization is transiently rotating faster than we expect, slower than we expect, with an average that comes out to be what we call the isotropic frequency or isotropic chemical shift. And if I wanted to generalize this to Hamiltonians, it would be exactly the same. I have the so-called Zeeman Hamiltonian that contains the B naught field and the chemical shift. And then I have some fluctuating Hamiltonian that's the sum of all these internal Hamiltonians for the dipole magnetic fields, chemical shift anisotropy from the electrons, etc. Quadrupole interactions if I have quadrupole. So everything inside is, actually I said, I got ahead of myself here. HZ, I'm just calling the static magnetic field. And then I have all the local fields. And when I do an average, the local fields have some isotropic part that survives averaging. And in solution, that will be the chemical shift and the J couplings. The dipole couplings have an average of 0, it turns out, which is why we don't see solid state NMR spectra in solution. All those enormous dipole couplings have averaged exactly to 0. And then we have the anisotropic parts, the parts of the Hamiltonians that average to 0, but instantaneously they're non-zero. And that will include, for example, the dipole couplings and whatever chemical shift anisotropies, whatever else is going on. And again, I can always make this decomposition, and all the isotropic parts that survive averaging, I'll lump in with H naught. And now H naught contains the Zeeman field, the scalar couplings, the chemical shifts. And the anisotropic local part that averages to 0 is what eventually is going to give rise to relaxation. So far we've ignored the anisotropic local part. Everything that we've been doing with the operators so far has been due to what's in H naught. That okay? So far? And then, because we have this enormous B naught field, we're extremely interested in behavior along the Z direction versus behavior in the transverse plane. So I can always then decompose this anisotropic Hamiltonian into part that have Z components and part that have transverse components. Again, completely general so far. And we'll eventually see that the parts of the Hamiltonian that are along Z will depend on operators that are like IZ and SZ, and the parts that are transverse will depend on operators like IX, IY, or I plus, I minus. Completely unsurprising to us at this point. So here, for example, is the chemical shift anisotropy Hamiltonian, and I'll use this as our example Hamiltonian for the rest of today until Anne introduces more complicated tensors. So, and we can pick out right away what the longitudinal and transverse parts are, because the longitudinal part is proportional to IZ, and the magnitude of that Z component of the fluctuating Hamiltonian is given by all these things. So you know what the square root of 2/3 is. Delta sigma is called the chemical shift anisotropy. It basically depends on how broad the powder pattern would be in the solid state, so that when the molecule is oriented in one direction, there's a different chemical shift than when it's oriented in another. And the orientation part is given by a spherical harmonic, where omega t here would refer to the spherical coordinates. So this assumes, again, we don't want to get into too much detail before Anne talks about tensors. So this assumes an axially symmetric CSA tensor. So we have a symmetry axis, and theta and phi orient the symmetry axis of the tensor in the laboratory frame. So our CSA looks like a football rather than a potato, which would be more complicated. Yep.
Can I truncate the transverse components like I did for the scalar coupling?
Not for relaxation. So if we talk about the first order spectra, then we truncate because of the effect of the huge B naught field. But here we're going to talk about relaxation. We can't truncate. We have to keep the whole Hamiltonian. So yeah, so we can look at the Hamiltonian and pick out what parts are longitudinal, what parts are transverse. We can see the dependence on tumbling because the angles theta of t and phi of t will depend on the orientation of the molecule in space. The spherical harmonics have the property that if we average over a uniform distribution in space, they're all 0. And you'll do that on the problem set. So that confirms that the average of this Hamiltonian is 0. It's the anisotropic part. The part of the chemical shift tensor that didn't average to 0 is the part that you would have truncated out. And that's now part of the isotropic chemical shift. So here I've just said, by inspection, the longitudinal part is everything that depends on the Z operators. And the transverse part is everything that depended on I plus or I minus or Cartesian operators. And I can write these in terms of frequencies. I can say the longitudinal operator has associated with it a time varying frequency that averages to 0. And that frequency then, by collecting up all the constants, is 2/3 gamma delta sigma B naught times the spherical harmonic. And that spherical harmonic will average to 0 over all space. Same thing with the others. I can have a frequency associated with y2 minus 1, y2 plus 1. I can convert to Cartesian frequencies if I want. And again, they all average to 0. The spherical harmonics that we need most often in solution NMR are the spherical harmonics of order 1, 0, 1, and 2. These are really what come up if we're talking about CSA or dipole interactions in solution. But there's normalization issues. I'll just warn you, if you are looking at papers, you have to figure out what normalizations are being used, because there's all sorts of normalizations. Anyhow, you know what these are. These are the orbitals. The L equals 0 is just the s orbital, it's a sphere. L equal 1 are the p orbitals. L equal 2 are the d orbitals. So the spherical harmonics just describe these distributions in space. And one of the reasons they're so useful for us is we're interested in rotations. We're interested in rotations of the molecules in physical space, rotation of the operators in spin space. But the spherical harmonics for describing rotations in physical space are really powerful, because if we rotate a p orbital, it stays a p orbital. Rotating a p orbital doesn't turn it into a d orbital. Rotating an s orbital, it stays an s orbital. So we're going to be able to eventually to simplify calculations by breaking things down basically into families of spherical harmonics that have the same rotation properties. It doesn't look like the d orbitals stay the same, rotate. I mean, it's not obvious, for example, that this d orbital turns into this one when you rotate, but they do. So you can change one p orbital into another under rotation, but p orbitals never become d orbitals. And that will be a great convenience after N. So some other qualitative things. So if we have transverse anisotropic components of the Hamiltonian, we can do a Fourier analysis and get out the frequencies of those fluctuations. And if those frequencies match differences in energy levels, then we can drive transitions, just like with a pi pulse. I mean, with an RF pulse. So the transverse components of the fluctuating fields can drive transitions. And that means those are the components of the fluctuating Hamiltonians that restore Boltzmann equilibrium. Because to restore Boltzmann equilibrium, we have to have transitions from alpha to beta to restore Boltzmann equilibrium populations. So transverse fluctuations lead to longitudinal relaxation. So it's a little bit at cross purposes, as it were. Unfortunately, these fluctuations are, of course, stochastic as the molecules are tumbling. So a molecule in one part of your sample has an instantaneous transverse fluctuation that's different from a molecule in another part of your sample. So there's no way that anyone knows to use these fluctuating transverse fields to generate a 90-degree pulse. So generating a 90-degree pulse, right, you have to have phase coherence across the sample. So we have to have some way of synchronizing the stochastic rotation of the molecule in solution to get anywhere. We don't really do that. So all they do is drive towards Boltzmann equilibrium. Of course, that will require some exchange of energy. If we have to go from alpha to beta, that requires some energy. That energy has to come from the surroundings. And because the surroundings are assumed to be infinitely big and at a constant temperature, that means this communication between the spin system and the surroundings eventually establishes Boltzmann equilibrium at a given temperature. The longitudinal fluctuations, as we already saw, change the precession frequencies. So if we have transverse coherences, random fluctuations along the z-axis will stochastically change precession frequencies, and that will eventually lead to dephasing and elimination of macroscopic coherences, and therefore that's what we call T2, the decay of transverse coherences. This has no effect on the populations. It doesn't need energy from the surroundings. So it's a purely phase randomization effect, no energy needed. There's a little contribution from the transverse fluctuations causing dephasing. And that's because in quantum mechanics, two energy levels can't have a precise energy, or two levels in a quantum system can't have a precise energy unless they have an infinite lifetime. For finite lifetimes, there's a Heisenberg uncertainty like broadening of the energies. So if the energies are a little bit uncertain, the frequency, transition frequency is a little uncertain. If the transition frequencies are a little uncertain, then the precession frequencies have some uncertain component, and that will lead to broadening of the transverse coherences. So that's called lifetime broadening in spectroscopy because the effect depends on the lifetime of the states. And eventually we'll see that if we have a two-level system, that contribution from the anisotropic components is R1/2, a very simple result. I should say, maybe I already said it and skipped over it. Maybe I didn't say it. So in physics, something that doesn't need energy is called adiabatic, and something that needs energy is non-adiabatic. So the longitudinal fluctuations cause adiabatic relaxation, It's just phase incoherence, no energy is needed. The transverse components need energy, so those are non-adiabatic contributions to relaxation. So recovery to Boltzmann equilibrium as a component from adiabatic relaxation, the recovery of Boltzmann equilibrium depends on the non-adiabatic relaxation processes because that needs energy. Dephasing has a component from adiabatic processes, just fluctuations along Z, and a contribution potentially from non-adiabatic processes through this lifetime broadening effect. The fact that T1 isn't infinitely long leads to this additional effect. For macromolecules, the adiabatic contribution to transverse relaxation is usually dominant, unless you have a huge amount of internal motion. So we'll talk first about a simple theory for adiabatic relaxation, and then later on, figure out how to generalize it for these other cases. And that's convenient because for macromolecules in solution, you can get a long way just by understanding the adiabatic part without worrying about the non-adiabatic parts, which are more complicated mathematically. All right, so longitudinal fluctuations drive adiabatic transverse relaxation. That's what we're going to talk about next. Transverse fluctuations drive longitudinal relaxation back to Boltzmann equilibrium and a small component of non-adiabatic transverse relaxation. And then the decomposition of the local magnetic fields or Hamiltonians in terms of linear combinations of the different operators in the spherical harmonics is useful because the spherical harmonics have really nice rotation properties. Now, tumbling in solution is stochastic. So we need some way of thinking about stochastic processes. And this is, of course, a kind of statistics. And we already worked out that the mean of our fluctuations are 0. We always set the problem up that way. So the mean isn't informative. And in statistics, the next thing you think of is the variance. So we can calculate the variance. We square the fluctuations and then average. And the square of the fluctuations, because this is a vector, means the dot product. And the fluctuations, if we assume the fluctuations along X, Y, and Z are independent of each other, then the total variance is the sum of the variance along each of the coordinates, X, Y, and Z. And for example, the variance in Z, we square the Z component, and that means squaring all these constants. We have the square of the spherical harmonic. We need to average that over all space. And if we ask Mathematica to do that, we get this answer. So there's some variance. And that's the variance in the precession frequency for transverse magnetization. That's not enough because we also need to know something about the time dependence of the fluctuations. So the variance is useful, certainly more useful than the mean, but we have to go and ask a statistical physicist, what should we use to characterize not only the magnitude of the fluctuations, that's captured by the variance, but something about the time scale of the fluctuations. And if we limit ourselves to stationary processes, then the first thing a statistical physicist will suggest is you look at the autocorrelation function of the process. A stationary process is one that doesn't have an absolute origin of time. And if you think about your molecules diffusing around in an NMR tube during an NMR experiment, you don't think that there's an absolute origin of time. You think mostly I can put the sample in the NMR spectrometer and go have a cup of coffee and come back and start my experiment. And it doesn't matter if I have a single espresso or a double espresso. If I came back and my sample had precipitated, I wouldn't think I'm going to rework relaxation theory to account for my precipitating sample. You would think I'm going to go back and figure out buffer conditions where the precipitation doesn't happen. Now, that's not always strictly true. You can imagine, for example, a kidnap experiment where there's a very fast laser pulse on the order of time scale of the tumbling, and maybe that does impose a real time zero. But outside of some fairly arcane experiments, you're going to be able to assume you have a stationary process. So absolute time doesn't matter, only time differences matter. So here then is an expression for the autocorrelation function of a stationary stochastic signal. We have the signal at some arbitrary time t times the signal at time t plus tau, and then we average that. And averaging could mean an ensemble average over lots of copies. Or in the case of our NMR sample, I divide the sample up into lots of small subensembles and average over each subensemble. Or it could mean a time average. So for a stationary system, that means it's also ergodic. So ensemble averages and time averages are the same. Sometimes, since time isn't important, absolute time, sometimes people will write 0 and tau, but they still mean averaging over all possible occurrences of that tau over all possible starting times. And tau is called the lag, and is the time difference between our arbitrary time t and t plus tau. Yep.
For the delta omega that you were looking at in the previous slide, right? Are we assuming that mean and variance fully define the distribution?
Hold that thought.
Okay.
I mean, that would only be true, right, if the distribution was Gaussian.
Yes.
And one of the main model systems we have, for example, is a two-site jump. And a two-site jump in general isn't a Gaussian distribution.
Right.
But hopefully by the end of today, we'll see whether we have to worry, when we have to worry about it. So the autocorrelation function turns out to be an even function of time. So C of tau is the same as C of minus tau. And if we write things out at time 0, we just have the square of the signal averaged, and the square of the signal averaged is the square of the mean plus the variance, which you can work out just by writing out the square and averaging term by term. So frequently, one might focus more on the autocorrelation function of the fluctuations rather than the signal itself. People move back and forth between those representations. And then something that comes out of statistical physics is that we expect that there's some characteristic time for fluctuations in the stochastic process called the correlation time. So if you think about a protein tumbling in solution or an RNA tumbling in solution, you think of that correlation time as something related to time it takes to rotate in solution. And the idea is that suppose we put a dot on our molecule and started it with the dot at the North Pole, over time, that dot's going to move around. For a very short time, we expect the dot's still going to be near the North Pole. So knowing that we started at the North Pole provides information about where we expect to find the dot a short time later. But a long time later, the molecule has tumbled many times over the full sphere, so that knowing we started at the North Pole gives us no information about where we ended up. We've lost all memory of the initial state, and the time over which we lose that memory is the correlation time, qualitatively speaking. And again, for us, that would be something like the rotational correlation time. But if that's the case, then here, knowing the signal at time t provides no information about the signal at time t plus tau. They're independent of each other for long taus, and that means we can average independently. So the correlation function when tau, our lag, is much, much longer than the correlation time, just becomes the average of the signal at time t, the average of the signal at t plus tau, but those averages are identical for a stationary process, so we just have the average squared at long times. So at short times, at 0, when the lag is 0, we have the variance, and at long times, we have the square of the mean. So in general, our autocorrelation function is going to start when tau is 0 at the variance of the process and decay in some way to the square of the mean. And how it gets between those 2 points depends on the actual stochastic process and the details of rotational diffusion, for example. For that, we have to know a lot about the stochastic process. But the 2 limits, variance when tau is 0, square of the mean when tau becomes infinite, are just general properties of a stationary stochastic process. So here's just an example. I started a large number of spheres, all with a dot on them at the North Pole, and then started random diffusion. After a short time, most of the dots are still near the North Pole, and then over time, the dots cover the whole sphere. The correlation function we're going to be interested in is going to be a correlation function of the spherical harmonics. Everything else in our fluctuating Z field were constants, right? They all come out of the average. So when I come back here, where did I have the Z? So here, for example, if I'm talking about the longitudinal Z fluctuations from the chemical shift Hamiltonian, I have the signal at time t depends on the spherical harmonic at time t. The signal at t plus tau is the spherical harmonic at t plus tau. I multiply them together and average all of these parts, the 2/3, the gamma, the delta sigma, the B naught. They're all constants, they factor out. And the important thing is the average of the spherical harmonics at 2 different times. That's the correlation function I care about. For y20, that depends only on theta as a function of time. It doesn't depend on phi, the polar angle. So what I've done here then is from that simulation, for each dot, I measured the polar angle, the deviation from the North Pole, calculated 3 cosine squared theta minus 1, multiplied them together. So here are the angles. So for a given, here's time. So I pick a time t plus tau. I calculate the spherical harmonics at those two times, multiply them together. Then I pick another time, add tau to that, do it again. So there's lots of combinations. If tau is 1 nanosecond, right, I have 500 copies that I'm showing you here of a given time and 1 nanosecond later. And then I average up all those combinations. And here's what I get. And red is the simulation, black is the theoretical calculation, because I know from theory that I should see 1/5 times an exponential for the tumbling time. That's something that comes out of statistical physics. So there's the autocorrelation function, basically for an isotropic molecule tumbling in solution with a correlation time tau c. It'll be a single exponential decay with time constant tau c. Depending on how one normalizes the spherical harmonics, this factor of 1/5 might not be there. You might just see the exponential and the decay by 1, or I could put in all those other constants and have the square of some frequency here. So it's a real problem in relaxation theory when you're reading papers that these constants can be partitioned in many different places and can be quite confusing. And sometimes people drop the constants they think you should know about. And then you have to figure them out by unit analysis as to what's missing. Here's another simple model, 2 site jumps between 2 states. And we have one frequency in state A, another frequency in state B. Before showing you the answer, let me say that what we want to work in for the time being is what's called the fast limit or the Redfield limit, in which the jump rates between A and B are fast enough that we only see a single average resonance line. So you tell me, in NMR, how do you tell 2 frequencies apart? Suppose we have 2 signals, omega A and omega B, and they're processing. If they have the same frequency, right, they just do this, they just go around together. If they have slightly different frequencies, what's going to happen over time?
One goes fast.
One goes faster than the other, but what does that mean builds up? A phase difference, right? So if we were looking at 2 signals, for short times, they look identical. And for longer times, they start to get out of phase with respect to each other if they have a frequency difference. So your ability to tell the 2 signals have a different frequency really means you can tell they have a different phase. If the frequencies are close, what does that mean you have to be able to do experimentally? Wait a long time, right? Because the phase difference is going to be delta omega times time. So to tell the 2 signals are different, you have to be able to observe them for times comparable to delta t, delta omega times time. And if the frequencies are very different, you learn pretty quickly that they're different because the phase difference builds up quickly. Now we have 2 signals, but we're jumping back and forth. So the system is in state A, you have frequency A. Now you jump to state B. right? And that disrupts your ability to tell the phase, because now the phase starts to get averaged between the two states. Every time you have a jump, you're now evolving at a different frequency. So you're limited, if there's dynamics, you're limited in how long you can observe a single state by the jump rate or the jump time. And again, with more work, we can figure out then that there's a correlation time that's the reciprocal of the sum of the two jump rates, the jump rate from A to B and the jump rate from B back to A. I mean, if you wanted to, you could go ask Mathematica, what's the eigenvalue of this matrix? And you learn one eigenvalue is 0 and the other is the sum of K1 plus K minus 1. So the only time constant in the problem is 1 over the sum of the rates. But anyhow, I can just tell you that now. So the correlation time limits how long you can observe. So if the correlation time is short compared to delta omega, you can't tell the lines apart. You see an average signal. So that means our observable phase difference is something like the ratio between delta omega and KEX. If delta omega is large, we'll see a phase difference. We can tell the signals apart. If delta omega is small compared to KEX, we can't tell the signals apart and we see a single line. So then this says the lines merge if the jump rate is faster than is larger than delta omega. And that's called the fast limit or the Redfield limit. And we could extend this to the powder pattern, say in solid state NMR, there's some width of the powder pattern, all possible frequencies for different orientations of the molecule. And the fast limit would be that the rate of jumps between different orientations is faster than the width of the powder pattern. So, or you could think of delta omega here as being something like the maximum frequency difference in the powder pattern. That turns out to be a really important limit because there are cases that we care about where this just isn't true. And right, large part of Hashim's lab makes their living and relaxation dispersion experiments were not in this limit. So, but for the rest of today, we're going to assume we're in the Redfield limit. A single average line. Here I've done, again, more simulations, random jumps back and forth. And here's the autocorrelation function. You have, again, a single exponential decay. So these are the two simplest models, isotropic rotation and two-site jump that give single exponential decays. More complicated models are going to generate more exponentials. So the math becomes more complicated, but the fundamental physics isn't so, really more complicated. So these two models will guide us a long way. So if tau is 0 here, what's the value of the correlation function? If tau goes to 0, PAPB delta omega squared. And when tau equals 0, what is that statistically? It's the variance. So the variance for a two-site hop between two frequencies is PAPB delta omega squared. In statistics, what's the symbol for variance? Just in a statistics book, what's the symbol for variance? Sigma squared. Yeah. But if you look in the literature, people pretty much call that quantity PAPB delta omega squared phi EX. And that's because I wrote it as phi EX in my first paper on relaxation. And I didn't yet know at the time it was the variance. And I'm always embarrassed now when I see phi EX in the literature because it should be sigma EX squared. On the other hand, you could argue maybe we don't need more sigmas in NMR. There's too many sigmas already. All right. Now, here's our model. That's all preamble. Again, I'm going to pretend I can divide the NMR sample up into little sub-ensembles. And each sub-ensemble, all the molecules behave the same. So they're all tumbling in synchrony in my little sub-ensemble as a Gedanken experiment. But every little box behaves differently. So what do we need to do? We should solve the evolution equation, the precession equation for each box, and then average over all the boxes to find out what our macroscopic sample does. So here's what a given box does. We just have the precession equation. M plus magnetization, the time dependence of M plus magnetization depends on the instantaneous frequency. And I can just have Mathematica integrate that for me. And here's the answer. And now I just have to average over all the boxes. And I have the behavior of magnetization. And the only tricky part is we don't really have an expectation as to what we think the average over a stochastic process will be that depends on the integral of a complex exponential with a fluctuating frequency. At least I don't have much intuition as to what that's going to look like. On the other hand, you already saw that I can simulate the two-site hop. So I can simulate the two-site hop a few thousand times and then just average to see what I get. Because obviously I can calculate the complex exponential and I can numerically integrate that in Python, and then I just have to average. So here's just 6 examples. So I have the two-site hop. Every time I'm in the A state, there's a little precession with omega A. And then the system jumps to the B state, and there's a little bit of precession in omega B. And then I jump back. And here then are the X component of the transverse magnetization. All the magnetization starts on the X-axis after the 90-degree pulse. But then the different sub-ensembles behave a little differently because they're stochastically jumping between A and B. So you can see they all start together. But if we compare, say, the blue finishes back up near +1. But if you look over at the yellow, it's near 0 at the end. The magnetization is almost completely on the y-axis. We're just looking at the x-axis. There's no relaxation here. Each little sub-ensemble is just processing forever and ever and ever, stochastically, just speeding up and slowing down. But they get out of phase with respect to each other because of the individual history. And here's a picture, hopefully. So what you see on the bottom are just those 6. They start out together, but over time, they start to get dephased with respect to each other. What's shown in yellow on the top is the sum of the 6. And what's shown in blue on the top is the sum of 1,000 or so individual runs. So every little sub-ensemble does not decay. There's no decay, they just are processing. But averaged over the macroscopic sample, you see the free induction decay. Because in time, you can see, for example, that the reddish and green have gotten opposed to each other. So they tend to cancel each other. And once we have thousands of these spread out over 2 pi, the average over the sample is 0. And that's transverse magnetization. It's just the dephasing of each little sub-isochromat of magnetization due to the stochastic process, in this case, the 2-site jump. There says what I just said. And if we play around a little bit, I can change the parameters of the simulation and see what happens. I can increase delta omega, so the variance goes up. I can change the jump rates, so tau c changes. And I can just play around for a while and see if I can make any sense of things. And here, if I do this for a bit, I can hypothesize that R2 then depends on the variance to some power and tau c to some power. And now this is like figuring out orders in chemical kinetics. So here I made, across the top, I have tau c, and the relaxation rate changed by a factor of 2. So I might think that R2 is linear in tau c. And then here, I left tau c the same and did something to the variance. The variance.
Crystal about heart.
I changed the variance and the rate changed by some amount. That seems sort of, did I do anything?
It looks like linear as well.
Anyhow, when I play around, I discover from these simulations that it looks like R2 is the variance in the Z fluctuating field times the correlation time. And that turns out to be the adiabatic part of transverse relaxation. The dominant effect for macromolecules in solution, R2 is variance times time. And you can get an awfully long way in solution NMR only knowing that. And this is one of the main results then of the first part of relaxation theory, is that the adiabatic part of transverse relaxation is the variance in the Z fields times the correlation time for the stochastic process. And as I say, I think that's one of the most important equations in NMR. If you need to know what your next tattoo should be, I highly recommend this so you don't forget it. Now, of course, before we could do these kinds of simulations easily, one had to do this mathematically. And we're going to do this mathematically because, or the way we do it mathematically, is going to be designed so that when we have to do the full problem, adiabatic and non-adiabatic relaxation, we'll be able to follow exactly the same steps. So it'll seem a little arcane. This is a pretty simple problem. And it'll seem like I'm doing it in a rather arcane way, but that's because it's going to make the next calculation way easier. So here's where we started. We have our precession equation. I separate the fluctuating fields into the average and the fluctuation. I call the average omega naught, the fluctuations average to 0. That's all we said. We have our differential equation here now, I'm going to switch to a rotating frame, rotating at omega naught, so that the omega naught part disappears. Again, similar to what we did. So here's the transformation. In the transform frame, which I'll call T, I multiply by e to the minus I omega naught, and I find a differential equation for the transform magnetization by differentiating using the chain rule. I know what dm plus dt is. That's my original equation. I plug in, and we've done this before, and I end up now with a differential equation for the transform magnetization in the rotating frame, and it just has exactly the same form as my starting equation, except there's no omega naught, because I'm rotating with omega naught. I just see the fluctuations. Good old rotating frame. And now I do the same thing. I integrate this equation and I ensemble average it. So this gets us back to where we were, except that now we're in the rotating frame, not the laboratory frame. So when I see an equation like this, and I'm stumped about what to do, I have very limited ideas. And one of the first ones is to expand in Taylor series and see if I learn anything by looking at the first few terms of a Taylor series expansion. If I don't learn anything from the first few terms, I'm going to give up on that idea and try something else. But for at least 50 years, I've been told that's the first thing you should, often the first thing to try. So I expand in Taylor series, and e to the a is 1 plus a plus 1/2 a squared plus 1/6 a cubed. So I just do that. And I've shown dot, 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 everything past the second term. So now I have a sum of some terms. And I've already made a first assumption. I snuck it past you, was that the ensemble average of the initial magnetization doesn't depend on the ensemble average later in time. That with somehow time is, reaching forwards. So I've split the ensemble average into two parts. One that's just the average of the initial state, and the other all the time dependence after the initial state. So, and all I've done here is say that I have the product of two integrals, and I've just rearranged the integrals and introduced some dummy variables. I have to keep the integrals separate. And finally, in the final line, the averages of a sum is the sum of the averages. And averaging is just addition. So addition commutes with addition. And integration is just addition. So averaging commutes with integration. So I've moved all the angle brackets inside of the integrations. And if you don't think right off the top of your head that averaging and integration commute, remember when you first learned to integrate, you had some curve and you drew a bunch of rectangles and you calculated the area of each rectangle, and then you added them up. So integration is just addition in a funny guise. So the average of 1 is 1. What's the average of delta omega z? 0. So I set the problem up knowing I wanted this first term to be 0. One of the problems with relaxation theory is it's a lot easier if you already know the answer. The people who did it the first time had to be smart. But I knew in advance that I wanted this term to vanish. And I set the problem up in a way that would ensure that when I got to this point, the first term in the Taylor series would go to 0. And then you see the second term is my autocorrelation function. If I extended, I would have correlation functions that would have 3 times in them, and then 4 times, 5 times, etc. So right at the end, we'll come back to that. Right now, we're going to say we just have, if we can ignore all those other terms, we just have the autocorrelation function. And we already know a little bit about the autocorrelation function for some simple cases, 2-site hops and rotational diffusion. So that's what we'll do. We'll worry about the higher order terms later. And then I can differentiate this equation. And here's the result of differentiating both sides. So before I had a differential equation where the averaging was outside, right? An equation where the averaging was outside of the exponentials and integrals. And by doing this expansion, I now have the ensemble averaging inside. And again, I knew that I wanted to do that to get to a autocorrelation function. So it looks like I've gone in a circle, I'm going in a circle, except I will have moved where the ensemble average takes place. And that's the critical part. Now, this isn't a differential equation because we have t here. T is part of the right-hand side. And that's a headache. However, at very long times, our autocorrelation function splits into the product of the autocorrelation function of the individual terms. Right? For times much longer than the correlation time, the average of the product becomes the product of the averages. And again, what's the average of delta omega z? 0. So at times longer than the autocorrelation time, the integrand becomes 0. And if I add in a bunch of rectangles of 0 area, what do I change the integral? No. So if I only care about times much longer than the autocorrelation time, I can extend the integral out to infinity because the autocorrelation function will already decay to 0, and integrating a bunch of zeros doesn't do anything. This is critical assumption. What's the time scale of, say, overall tumbling of a protein in solution? Some nanoseconds, right? Ubiquitin, 3 or 4 nanoseconds. So the stochastic times in solution that we're interested in are nanoseconds. What's the time you're interested in when you measure a free induction decay? That may be a little slow, microseconds. If you look at the sampling, if you look on what Brooker calls the dwell time, when you're recording a proton spectrum, it's going to be microseconds, right? Because that has to be 1 over, I can't see what that says. Yeah, that's a little slow because we have to sample 1 over the spectral width. So that's going to be something like tens of microseconds. So we care about tens of microseconds. The tumbling time of a protein or an RNA is nanoseconds. So the autocorrelation function for overall diffusion is going to have decayed away long before the time scale we're interested in. So this assumption is going to be very good, as long as we're talking about diffusion timescale processes. If we start to talk about slower processes, jump over a rotamer barrier in a protein, then this might break down and this theory doesn't work. So, oh, I did things in another order. The other problem is we have the magnetization at time 0, not time t. If we wanted a differential equation, we would have the derivative of magnetization with respect to t on one side and the magnetization with respect to t on the other. We don't have that. That's trivial. We just assume that we're talking about time scales short enough that the magnetization hasn't decayed very much so that we can approximate this. And then you say, I'm really interested in times much longer, but then we do Simpson's rule again. We say, I calculate relaxation over a very short time, longer than nanosecond, and I've decayed a little bit, and then I use that as the starting point for the next little time, and I work my way down by Simpson's rule. And once I do that once or twice, I realize that I don't have to worry about this assumption at all. So I can replace 0 with t. And then the critical assumption is that I'm interested in times much longer than the correlation time of the process, so I can extend to infinity. So I can't tell you in this theory how the spins relax on a nanosecond time scale. If I wanted to answer that question, I have to do something completely differently. I can't tell you in this theory about relaxation of spins subject to slow processes on the microsecond to millisecond time scale, because the autocorrelation functions won't have decayed to 0 at that point. So it is sometimes called the coarse-grained time scale. I can't ask about fine details in time, only coarse times. But I now have a differential equation for the ensemble average magnetization, the magnetization over my sample. I'm in this funny frame, so I can transform back out of the laboratory, back to the laboratory frame. And when I come back to the laboratory frame, here's what I have. I have precession with omega naught, that's just normal precession. And I have this integral. And I know what I expect are the block equations. I expect precession at the Larmor frequency and decay with R2. And by inspection, this must be R2. At R2, we're only talking about adiabatic part. The adiabatic part of R2 is the integral of the autocorrelation function. It's a little more general than what I said earlier. This is the bit about stationary. If our autocorrelation function decayed as a single exponential, it would decay as variance times a single exponential decay. And in that case, we can just do the integral. We know how to integrate an exponential, and we get that R2 is variance times correlation time. What we worked out by looking at the simulations, what we guessed by looking at the simulations. So, oops, something's wrong with the LaTeX. I'll have to fix that. So we have, for a single correlation time process, R2 is variance times correlation time. More generally, R2, the adiabatic part of R2 is the integral of the autocorrelation function for the Z fluctuations. A nice simple result. But again, we did it in this mathematical way because it's going to be useful for us in the future. So just to recall, we transformed into the rotating frame. We integrated the equation. We ensemble average, expanded in Taylor series, threw out the high order terms, threw out the terms that average to 0, and then differentiated, converted back to a differential equation by assuming this coarse-grained time scale. And we're going to do the same thing after and, except we're going to have to work with a Hamiltonian that has fluctuations in all directions, not just the Z fluctuations. What we'll follow the exact procedure. So it's a really good idea to review the main steps of this procedure because it's just algebraic. Whereas when we do it before, we're going to be doing it with operators, which will be more complicated. So here was the Z component of the CSA Hamiltonian. Here's the frequency. We already said for tumbling, we know the autocorrelation function. Just plug in, and there's the adiabatic part of CSA transverse relaxation. And if you look this up in a book, you will find it. If we did some model calculations here, for some model calculation, the adiabatic part comes out to be 22 per second. If we do a full calculation with what we learn later, for this model, we'll get 22.5. So the non-adiabatic part is 0.5 per second. If you're trying to decide whether your experiment is going to work, that 0.5 isn't going to be very important to you. The dominant part is the adiabatic part. Yep.
So to the last expression, delta sigma square omega naught square tau c, does this mean that my protein will have larger line widths and stronger magnetic fields?
Sure, CSA goes up quadratically with the field. That's why doing phosphorus at 1.2 gigahertz isn't going to be very popular. And when it comes to TROSY, the nitrogen TROSY experiment works by trying to match the dipole relaxation, which is independent of field, to the CSA relaxation, which is scaling up quadratically. And then you work out that you need a 900 megahertz NMR machine. And that was a lot of the stimulus for development and purchase of 900s was that. Yep. Yeah, so already you learned something important about relaxation. CSA is quadratic in the size of the magnetic field. So here are three assumptions. We can neglect the higher order terms in the Taylor series expansion. The second one isn't important because we can do the Simpson rule to get out to longer times. And then the important one, we have this coarse-grained time scale. Now we're past 2:30, but I just want to finish. I'll skip a lot of the math. We can ask what happens with the higher order terms. So first of all, the odd order ones we can show all tend to vanish, and we're left with the even order ones. And if we assume for a moment the Gaussian process, then the fourth order autocorrelation function can be factored into a product of our normal correlation functions. And then we can crank through to find out what the consequence would be when we do this integral. And again, if we have a single exponential decay, I can work out the integral. Here is what the integral ends up giving. I do this for all of the different products. I get a result. And then I know the second order result. And I can see by comparison that the fourth order result is much smaller than the second order result if the variance is much smaller than the square of the autocorrelation function. Or if I take the square root of both sides, this says if the standard deviation in the fluctuations times the correlation time is much less than 1, the standard deviation is like the width of the distribution. It says delta omega times correlation time is much less than 1. That's the Redfield limit. So if the powder pattern has collapsed to a single average line, the higher order terms in the Taylor series are negligible. If that doesn't happen, and that's the Redfield limit, that's the fast limit. So this theory is accurate in the fast limit because the higher order terms become negligible. If we're not in that limit, your first thought might be, maybe I should just add a few more terms into the Taylor series expansion, but that doesn't work. It turns out that once the fourth order term is not negligible, the decay as you move to higher and higher order terms is very slow, and it's just not practical. So we just have to switch to something different. Once we're out of the Redfield limit, we need a different theory. We can't really patch this one up in any meaningful way. But it's certainly nice that this limit where this theory approaches is the same limit that we saw kind of right in the beginning, that to tell two signals apart, we have to be outside of this Redfield limit or collapse of two lines or n lines into a single line is sufficient for this theory to work. It's a nice closing of the circle. There's more you can read. I've said all this along the way, particularly about this coarse grain timescale and when it fails. And here then, right, we can then estimate line widths with this simple formula, or we can use something more sophisticated, but this gets us a long way. Here's tau c for a rigid sphere with some radius. You might take for your protein, get the radius a little larger by adding a layer of water. But basically, we can get an idea of line widths versus tau c. That's, of course, important to you. Our cozy type experiments, right, transfer from the J coupling in a cozy or an inept sequence depended on the sign of the couplings. So while you're trying to build up coherence, relaxation is causing decay. So here's what happens. If there's no relaxation, you just see the sign belt. We can adjust our evolution time to transfer all the coherence. As R2 gets larger, we can transfer less and less of the magnetization because it's decaying away faster than the J coupling builds up. And this tells you pretty much everything about modern NMR. In the beginning, you just had protons. You worked on small molecules. You got the bigger molecules. You had to switch to heteronuclei with bigger J couplings in order to beat this equation. And then, once you've used up all the J couplings, the only thing you can do is try to make R2 smaller. And there's only two things. You can either make tau c smaller or you can make the variance smaller. So smaller tau c, we can move to higher temperatures. You can break the problem up into smaller pieces and solve the pieces one by one. Smaller variants, you deuterate or go to Trozy experiments. And you know, there's not really, these two equations are basically it. So to change, you know, what's feasible by NMR is you have to figure out, given that there's no more J couplings, you have to figure out how to beat the relaxation equation. And you get very famous by figuring out a new way of addressing one of those two terms. The non-adiabatic part is true, you know, isn't very big. So everything is here. Make the variance smaller or tau c larger. Now, T2, R2, is caused by this random phase evolution. That's just chemical shift. You know how to refocus chemical shift. How do you refocus chemical shift? The spin echo. So with transverse relaxation, if the dominant adiabatic part is just chemical shift evolution, why can't you just put in 180-degree pulse and refocus the precession, and then R2 goes away, and you can do an 8-dimensional experiment and graduate in a week.
Because it's stochastic, right? It's a random phenomenon, which means that the amount that have dephased before the echo is not the amount that have dephased after.
Right. The spin echo means that the phase accrued in the first half of the spin echo has to be exactly the phase accrued in the second half. And if that's true, you get an echo. If that's not true, you don't come back to the right place, right? So why doesn't it work in this case?
Because those phases have changed, right? Because the evolution frequency has changed because of stochastic fluctuation.
Right,
Yeah, random.
right. But suppose Brooker built a probe where I could do a 180 in 1 nanosecond. It takes my protein 10 nanoseconds to rotate, right, and change the frequency. So if I had a 1 nanosecond spin echo, wouldn't that work?
Relaxation is not phase coherent over the sample.
Right, but the spin echo doesn't care as long as in each sub-ensemble the phase was the same. It wouldn't matter that in different sub-ensembles it was different phases, they would still come back. It would work. The only problem is Brooker can't build a probe with a 1 nanosecond 180. And if they did, the amount of power would probably melt the probe and dim the lights in the building. But it would work. I mean, the problem is that the time scale of the fluctuations are faster than I can apply a 180. So then there's different phases on each side, as you say. But if I pulsed faster than the stochastic process, it would work. And we call that relaxation dispersion, right? In cases where we have slower processes. On a Brooker probe, you can get a pulse on the order of 10 microseconds. So if you're talking about a 1 millisecond process, you can pulse before the spins have a chance to dephase very far and then get them back in the echo. And then you can just finish. Here's a simulation in which I have the free precession. In the middle, I have 180s at a relatively slow repetition rate. And here I have the 180s at a fast repetition rate. In the fast repetition rate, the spins never accumulate much phase angle, so they can't ever get too dephased from each other. And you can see if I take the sum here, I'm going to have substantial signal along the x-axis, whereas in the middle, I'm not going to have so much projection onto the x-axis. And here I get a lot of dephasing, just like before. And if I do it then 1,000 times, there's the free precession decay, normal R2. Here's intermediate pulsing, and there's some dephasing, but I've reduced it. And here's very fast pulsing, and there's hardly any decay at all. So that's right, a CPMG relaxation dispersion experiment. So the idea works. It's just a matter of time scale upon which I can manipulate the spins relative to the time scale of the stochastic process. And this is to say that all of NMR depends on relative time scales. How fast something is happening relative to something else. In this case, the time in which I can do a spin echo relative to the stochastic change in the properties of the spin system. So that's another qualitative thing not to forget. NMR depends on relative timescales in a very profound way. Okay, sorry we ran over, but I wanted to finish this so that you're ready after Anne to then try to generalize this. Of course, when we generalize, there will be one more fundamental conclusion, and then a lot of numerical calculation, because of course, if you're analyzing relaxation data or want to calculate T1s, you have to calculate the full theory. But of course, that's all coded up in spinach these days. So you don't have to do it by hand anymore. But the full theory will tell us something of important conceptual importance. So I've gone over, I don't know if people want to take a short break and talk briefly about problem set 3 or leave problem set 3 for after Anne. That's kind of up to you. I can stay around and I'll just see who stays. And if everybody disappears, then we'll just start worrying about problem 3 next time I'm here. But go back over this. I mean, if you understand today's lecture, you understand, probably 75% of relaxation. Any questions online?
Yeah, question.
Yep.
So you explained how 180 pulses, by varying the frequency of the 180 pulses, you're able to look at the dispersion relaxation. Can you sort of give an intuitive explanation of how the same thing works under spin lock?
So the idea when you turn on a spin lock is if the spin lock is strong enough, if the magnetization in the A state percepts around the effective field in the A state, the vector sum of omega 1 and omega A, and same thing for the B state. So there are different tilt angles in their processing. And if they jump and start to process around a new cone, they gradually get all confused and dephased. But if you make omega 1 large enough so that they're pointing in essentially the same direction, then jumping back and forth has very little effect on what happens as they process. And in the limit of omega 1 being completely dominant, they'd be processing just around omega 1, and then jumping between them would make no difference at all. So it's still a kind of dephasing, but it's a little more complicated to visualize because you're jumping between precession on two different cones. And as you make the two cones more and more identical, the effect of jumping goes away.
And
But every so often I try to develop a nice graphical picture of that, and I haven't.
and why is the Darwin law reaches faster time scale limits than CPMG?
Oh, just is because when we go off resonance, right, omega 1, the effective field is the vector sum of omega A and omega 1. So given that you have some limit on omega 1, then you go off resonance, kind of an arbitrary amount. It doesn't work forever because the tilted frame comes up and up and up until you're on Z.
Yeah.
But for a while, you can just keep making the effective field larger by going more off resonance. And
Okay.
whereas in the CPMG, you're limited more or less by how strong an RF field you're willing to put through your probe. And Christian Griesinger is pretty courageous, but most people aren't quite as courageous as Christian.
Superior did his PhD to develop the fast range. Yeah, basically, it making more stronger.
Fiber.
Yeah. Extremes, of course, extremes. And if we have 3 point, like this is all about the 2-point jump. So if we have another state, like 3 states,
Sure.
then our assumption be still working for the 3 state system?
So yes, so the fast limit would say you have 3 signals. In the slow limit, you would see 3 resonance lines.
Right.
And then if they've collapsed into a single line, then this theory applies. Of course, you have to calculate the autocorrelation function for a 3-site hop rather than a 2-site hop. But that's just a mathematical problem. The critical assumption, it doesn't matter how many sites you have. And if you think about it, for diffusion, you can imagine that as an infinite number of sites where you're doing infinitesimal jumps. So the number of sites isn't important. It's just that the time scale has to collapse all the lines into a single resonance line. And if you think about this, of course, in Ashim's lab, you don't want to be in that limit. There's more information available if you're not in the fast limit. So your goal for relaxation dispersion is to move away from the fast limit.
Right.
And so you could have the situation, where you have 3 states that exchange between 2 is in the fast limit, and exchange to the other one is slow, just depending on the chemical shifts. And that can lead to situations where, for example, 2 states could be treated as an average state in slow exchange, with the other state. You're also going to have situations, for example, if you're looking at 0 and double quantum coherence, where now you're looking at the sum and difference frequencies between the states. And the double quantum coherence might be in slow exchange, and the 0 quantum coherence in fast exchange. For the same time scale, one of those, is the difference frequency, and you've collapsed the frequency difference to some extent. So the adiabatic part, just depends on variance. So as long as you collapse to a single line, it's just really a matter of variance and time scale.
So
Yep.
is hopping the only mechanism of exchange?
Pardon?
Is two-side hopping the only,
Oh, no,
can have continuous process?
sure, you can have anything. But again, for our theory, if whatever the situation is, if it's collapsed to a single line, then this theory works. Our only difficulty is to figure out what the autocorrelation function looks like for that stochastic process. And of course, then, for example, Mickey Scher published a paper long ago assuming that there was a continuous Gaussian distribution of shifts along some path. And he calculated the autocorrelation function. Of course, these days you might say, I run some kind of computer simulation for some arbitrary energy surface where I have a ball rolling around on the surface, and each position on the surface corresponds to some z component. And then I just numerically calculate the autocorrelation function. And then it's only a matter of how creative I am in thinking up what the surface is. So the problem of variance times time scale doesn't care at all what the physical system is, as long as it's fast enough to collapse the lines, which is a great part of the theory, which oh,
How variance plays different role
In solid state, NMR, something.
right. So when we come to solid state NMR, of course, there's the problem that you don't have this nanosecond time scale rotational tumbling that almost always guarantees, at least for chemical shift anisotropy, dipole-dipole relaxation, quadrupole relaxation, that the fast limit applies. And outside of the fast limit is really what we call these kinetic processes, chemical exchange jumps over barriers. But in solid state NMR, you have no overall tumbling and much more limited local librations that in general aren't averaging anything over isotropic space. So there's a lot more complicated situation. For the slower timescale processes, things that we would think of about as corresponding to relaxation, dispersion, and solution, hopefully between Anne and me, you'll see that those aren't so different between solution and solids, except for the fact that you have the time scale of MAS, which can be on the same time scale also as the hops and say the spin lock or 180-degree pulses. You have to worry about the interaction with the MAS frequency, which we don't have to worry about in solution because tumbling is so much faster than these other slow processes. On the fast time scale, people apply many of the same Redfield type theories, but it's somewhat murkier the extent to which they're really the right thing to do. And hopefully Anne will have a lot more to say about that. So as usual with a hard question, I'm saying, Anne will answer it. So hold on to that question for Anne. And since it's now well after 3, I suggest that we just wait on problem set 3 until I'm back. But if you're looking at it over the next week and have questions, I'll have emails, so just email questions.
Thank you.
I'll see everybody in a week.
I'm excited for Brazil.
I still have a lot of course prep